Welcome to the lecture on Shapley values. Today we learn what game theory is, or at least get a basic understanding. We want to understand the concept behind cooperative games and understand the Shapley value in game theory. So game theory is the study of strategic games between players, where game refers to any series of interactions between actors or agent with gains and losses of some kind of quantifiable utility value. So it often helps to think of a game as in a board game or a sports game, but it doesn't have to be like that. It can also be some kind of economic game, or we'll see later that it can also be related to machine learning. And the cooperative games mean that for all possible players P, so that's a set capital P, and the players are 1 to P, that each subset of players S forms a coalition, and each coalition achieves a certain payouts. So the players in S play together and gets a payout in the end. And the value function is now a function that maps from all possible coalitions. So that's 2 to the power of the size of P, so the number of all possible players, and it maps to a real valued payout or gain, but we'll just call it payout. And V of S, so is the value function, is then calculates the payout of a coalition S, and the payout of an empty coalition always has to be 0. So if there are no players in a coalition, then there won't be any payout. But some players might be contributing more than others. And the goal of Shapley values is to fairly divide the total achievable payout among the players according to what they contribute to the game. And we call the individual payout per player phi j, where j is one player, and later we'll call that phi j Shapley value. So let's start with an example. So we have 3 players. We have the red player, we have the yellow player, and we have the blue player, and they all contribute something to the game. And if they play alone, they get a payout according to the stars here at the top. So a coalition of only the red player will get 1/6 out of the total payout, and the yellow one will get 2/6, and the blue one 3/6. And in this first setting, we'll study a game without interactions. And that means that if you add the payout of the red and the yellow player, so that's 1 plus 2 is 3, so it just adds up. The same holds here for the yellow. 2 plus 3 of the blue ones is then a payout of 5. And if you do that for all coalitions and they all just add up, this is a game without interaction. And here to calculate the fair payouts is trivial, because you just take these numbers here, these payouts, and the blue one gets half of the total pot, and the yellow one gets 2,000 out of 6,000 euros, and the red one gets only 1,000. And that's fair because they all contribute. Also in the other coalitions, they all contribute the same as their original one. But it gets more complicated with interactions. So with interactions here means, for example, that you can't just add up. So the payout of just the red one would be 1 star, so 1,000 euros, and of the yellow one would be 2. Adding up, this would be 3, but those 2 players together achieve a payout of 4. But on the other hand, if you go from only the blue to the blue and the yellow, it doesn't change anything to the payout. So the payout of the yellow one to that, the contribution of the yellow one here is 0. So one example from sports here would be if a team already has a great goalkeeper in football, so the blue one, and let's assume that the blue goalkeeper won't get injured, and you add another good goalkeeper, so the yellow one, but you can only have one goalkeeper on the pitch at a time, so it will not increase the winning probability of the team if you add the yellow goalkeeper to that team or coalition. And that's why then it's unchanged from the team with only the blue goalkeeper. So in summary, it's unclear how to fairly distribute payouts when players interact. So those numbers here are not so easy to calculate. And with Shapley values, we want to answer the question, what is a fair payout here? And when we start with the yellow player, the idea is to compute the marginal contributions of the player of interest across all different coalitions. So which coalitions do we have? If we start from the bottom, we have the empty one. So we don't have any players in the coalition, and now we add the yellow one. Or we could already have the red one, and now we add the yellow one, and so on. And here at the top, we already have the red and the blue one, and we add the yellow one. So we compute the total payout for each coalition, and always compute the difference in payouts if we add the yellow player or not. And now we average this marginal contributions using appropriate weights. That's the whole idea of the Shapley value. But each marginal contribution is weighted because you have several orderings. So there are two ways now to calculate that. You can do that. That's, I would say, the more straightforward way here is you could consider all possible orderings. So for the set of the blue and the red one, you could first add the blue one and then the red one, or you could first add the red one and then the blue one. And you have to count both. And if you do that, that's why we call it via orders, because you consider all orders, or you consider just the unique sets, and then you would have just one set with the red and the blue one, and you will just give it a weight of 2 because there are 2 possible orders in that set. And it's easy to calculate for the coalitions with only one player because you cannot have any reordering. But if you have the empty set, you can also have the case where the red one enters first and the one where the blue one enters first. So you also give it a weight of 2. So if we start with the set version, so the one here on the right, where the order doesn't matter, then the definition can go as follows. So we assign a payout value to each player according to its marginal contribution in all possible coalitions. So we have our value function, and we take coalition S and add the player J and calculate the value function. And we calculate the value function for the coalition S without the player J. And the difference is the marginal contribution of player J to a coalition S. So it measures how much a player J increases the value of a coalition S. And now we average the marginal contributions for all possible coalitions. So we form all possible coalitions, but always without the player J, and now do the calculation from the first step. But the order, as we have just seen, the order of how the players join the coalition matters. So we have to do some weighting depending on the size. And for that's then the set definition of Shapley values. We take all possible sets of players without the player J. We take the marginal contribution, so the difference in the value function, and we calculate the appropriate weight. And we'll see in a few slides how to calculate that weight exactly. If, on the other hand, we want to do the order definition, we take again all sets of players of S without J, but we look at all orders. So what we do now is there are there P, so the size of P, so how many players do we have, and the factorial of that is the possible number of orderings. So we have to divide by that, and then we sum over all orderings, and now we again take the marginal contribution, so the value function of the set with then player J and of the sets without, but here note that small tau, and that is because we have to consider different orders. So the Sj tau is the set of players before player J and in order tau. So easiest to explain by example. So let's say we have the players 1, 2, 3. So we calculate all 6 possible orderings of those players. And now for each order, so let's say we have 2, 1, 3, and player of interest would be 3. We have before that we have the players 2 and 1. So in Sj tau go 2 and 1. And if we have this ordering and the player of interest is 1, we only have the 3 in front of it. That's why here Sj tau is 3. And for the same ordering, if we're interested in 3, then there's no player before. So Sj tau is the empty set. And we do that for all possible orderings, and that also gives us the Shapley value phi j. So this is then the marginal contribution of orders that, but the set S1 and 2 is summed twice. So we have 2 orderings where 1 and 2 are before 3, and the contribution of player 3 to these collisions should always be the same. And that's why we can write it also in a way where we have a weight of 2 over 6 of the same marginal contribution. We'll see in a minute how to calculate those weights from a little bit more complicated cases. So first, the order and set definition are equivalent. So we will always end up with the same Shapley values, but the set definition is faster to compute. We'll also see that the order definition also has an advantage. So they're equivalent because the number of orders which yield the same correlation is calculated by this number. So to explain that, order all players, so let's hear this down here, put all players in one row, and we have somewhere in between our player of interest J. And now we have the set of players already in a coalition before that player. So to the left, we have the size of S, because all the players in the coalition S are left of the player J. Player J is always only one player. And then to the right, we have all remaining players. So that's the size of P, so all players, minus the number of players in the coalition, minus 1 for J. And now if you want to have the possible reorderings, or possible orders of all the players left of player J and right, you will just add the factorial, because you always have the factorial as number of orderings, and you also do that on the right. And that gives us here this number, which we'll use for, which you see here in the weighting. That was this number here. So the advantage of the order definition is if we do an approximate Shapley values, we will see later how that works, we'll sample permutations. So we won't take all of them, because if you have many players, they are just too many to calculate in realistic time. So you just take random samples of that. And for that, you need to randomly sample from the orders. So now you create a fixed number of m permutations. So you randomly sample them. It's a subset of all possible permutations. And you just calculate the Shapley values for those, because that's faster. So let's look at the weights again in an illustration. So you have 3 players. That gives you 6 possible orders, because factorial of 3 is 3 times 2 times 1 is 6. And you can do that via orders. So you start with the blue and the red, and you add the yellow, or you start with the red and then the blue and then you add the yellow, and so on. You have, for the sets with only 1 player, it's easy, you don't have different orders, and you have the empty set where you also have 2 possible orders. So you can start with the red or with the blue one. And you could do the same via set definition. But now the first 2 together in one set. So that's the red and the blue, and the order doesn't matter, but because there are 2 possible orderings, you have a weight of 2. And same here for the empty set, you can also have 2 possible orders. That's why the weight is 2. And if we now want to, so if we go back here to the example in the beginning, so remember here it was easy to calculate, but here with interactions, we don't know the numbers here, and that's what we want to calculate now. So remember that red is player 1 and contributes and alone contributes only 1, and yellow is player 2, contributes 2, and blue is player 3 and contributes 3. All right, so if we now look at all possible orderings, so let's start with 1, 2, 3. So we have the empty coalition, so no player gets a payout of 0. That always has to be true. And if we now enter player 1, that's then only the red player. That was 1 star, so it is 1,000 euros. If we now also add player 2, then we have a set with 1 and 2, and that gives a payout of 4,000. So remember, just going back again, that is then this set here, and they together have 4,000 euros as a payout. And the full coalition always has a full payout of 6,000. So here now the contribution of the first player was the difference between these 2, and that was 1,000. And we do that for all sets. So in the second, for all orders, sorry, for the second ordering, we again start with the empty set. Then we add player 1, gives us 1,000. Then we add player 3, that gives us then an additional 3,000. But player 1 went in here at the beginning, so the difference is 1,000. But for example, down here, where we have 2, 3, 1, player 1 just entered here at the end, and now the difference here was 3,000. And we just average those values and calculate a Shapley value of about 1,800. And we can do the same for player 2. So now we look at all changes of the coalitions where we add player 2. So here it's 3,000. Here it's 2,000, and so on. And this at the bottom here was that example where player 2 enters and it doesn't make any difference. So that contribution here is 0. And that's why in the end, the Shapley value of player 2 is the same as the Shapley value for player 1. But that's basically just a coincidence here that it's exactly the same. For player 3, we see that in the first order, player 3 enters last, so 2,000 euros. Here the difference is 3,000, and so on. And so player 3 gets about 2,300 euros as the Shapley value. So now we have calculated our fair contributions. So player 3 still gets most of it, but even though there the contributions of the single players are quite different, their total payout is not so different, because it seems like, for example, the red one brought in some unique expertise which the others didn't have, or something like that. So now we can calculate the fair payout. So, but the question is, what is actually a fair payout solution? And for that, we need some axioms. And for Shapley values, we have, I think, 4. So first, the efficiency. So if a player contributions add up to so all player contributions always have to add up to the total payout of the game. So this was the total payout, 6,000 euros in our example, and the Shapley values of all the players have to add up to that total payout. So there cannot be any payout left, and there can also be no payout coming from nowhere. And we have symmetry, meaning that 2 players, let's call them J and K, who contribute the same to any coalition get the same payout. So if the value function for the coalition S, including the player J, and is the same as the value function for the coalition S, including player K, for all possible coalitions without J and K, then the Shapley value should always be the same. That's a symmetry. Then we have the dummy and null or null player. So a payout is 0 for players who don't contribute to the value of any coalition. So if the value function is the same, no matter if player J is in there or not, for all possible coalitions, then the Shapley value is 0. And we have additivity. So for a game with combined payouts, where we can combine the value functions or payouts together, then the payout is also the sum of payouts, and the Shapley values can also be added in the same fashion.